Okay, so welcome to this NPTEL course on elements of vibration engineering, and my name is Ashish K. Darpe. I am a faculty in Department of Mechanical Engineering at IIT Delhi, and so this course is essentially designed for undergraduate students in maybe third year or a final year of their curriculum, but those with the basic understanding of engineering mathematics as well as engineering mechanics can do it in even in the second part of their later part of their second year studies. But at the same time, graduate students who might have missed this particular course in depth during their undergraduate studies can also find this quite useful. And from the practical perspective, this particular domain of dynamics is very relevant for the current engineering design, as we shall see and discuss in the course of introductory part of this particular course. So, it is quite practically very relevant course, and I have been teaching this course at IIT Delhi for several years. And before giving you the course content of the course, I usually start it by giving basic background of why we should be at all studying this as a separate course when we have already learned part of the dynamics of machinery. So, we will have a brief overview of this course or this subject as a whole, and then I will highlight what are the contents of this course and what are the course objectives. So, we shall start first with an example which essentially tells us as to the significance of in-depth study of vibration as a phenomena and how it goes well beyond the basic design process. Okay. So, the practical example I would like to start with in this course is a wind turbine, as you can see here, which consists of a columnar structure. On at the tip of it lies a structure called nacelle, which houses all the rotating equipment starting from the bladed rotor and all the way on the back side, finally ending in a generator. So, this nacelle basically houses the most important mechanical equipment of this wind turbine. And if we want to design this the column of this wind turbine, the basic process which we already have learned through the first course in mechanics or solid mechanics, strength of material to be precise, is making a small model of this wind turbine like a column, as you can see here, and sitting at the top is the nacelle which you see here, and then look at how the sizing of this column will be based on the weight of this particular element, the nacelle. Now, to start with, let us assume that the nacelle can be modeled as a dead weight at the top of this column, and then if that is the case, the basic strength of material has told us that if I want to design this column, particularly the cross sectional dimensions of this column, that is what we would like to do. We would look at what are the stresses which will be induced in this column based on the weight which is acting from the top. Now, presuming again that the designers have taken some care that the center of mass of this entire system is coaxial with the column, the simplest way to size the column is use our basic relation between the stress induced from the load which is acting on the column or on this structure based on the cross sectional dimensions. And if we assume it to be a solid structure, circular one, then this is the way we would go about finding out the stress in this column. So, given the load and given the allowable stress, the diameter, which is the size of this structure, will be straightforward answer. I mean that is how you will find out the diameter of this column. If you want to go a little further, you would definitely would like to see whether this will buckle. So, the buckling of the column can be accounted for. If you know the flexural rigidity of this column, you can find out what is whether this load will be sustainable in terms of the buckling load. However, this all will be the very basic design process based on the assumption that the load which is acting on the column is a static load as such. But I guess all of you will be agreeing to the fact that this is not a static structure as such, it is a rotating equipment. At the tip in the nacelle, you have this rotor which is spinning at certain speed, and the dynamics of machinery has taught us. Those who have done kinematics and dynamics of machinery would immediately recall that this rotating equipment will have some residual unbalance in it, and that residual unbalance is going to be responsible for the generation of a dynamic force in the nacelle, in the rotor. So, you basically would then start looking at the possibility of a dynamic force which will generate at the rotor, because these blades are quite long, and any practical rotating system will have some residual unbalance. A force which will act on this bladed plane is going to be a centrifugal force based on the unbalance, net unbalance in the rotor, and will be dependent on the square of the rotational speed. Now, this force is going to be varying with time. So, it is a harmonic force acting at this particular location in the rotating shaft, and so we can expect it to be a harmonically varying dynamic force, and that dynamic force is going to create interesting forcing on this structure. And we all know that since this force is acting at a distance r from the axis of the column, it is going to create a bending moment about this axis and would excite the column. Okay. So, there would be a bending moment acting on the column at the tip, and in addition, of course, you will have a compressive force which is also time varying. So, apart from the dead weight, the rotating shaft is going to create a fluctuating longitudinal force and as well as the bending moment. What also interestingly this forcing in this particular plane will do is, it is also going to create a twisting moment, a torsion, and that is going to be this m e omega square into the arm of the force. So, this is going to be a twisting moment which is going to be generated, and it is also going to be a function of time, because as the blades rotate, the direction of this force is going to change. So, all of this is all going to create a fluctuating forces, the compressive load, the bending moment, twisting moment on the column, and that is going to create time varying forces on the column. All right. And if we now want to look at the stress induced into the column, we would definitely know from our basic strength of material studies that at the root of this column we are going to have maximum stress induced, and we will have to look at all the compressive stresses which are going to be same throughout the cross section because of the force acting the compressive force, but the bending moment is going to generate different kind of a stress pattern across this line. On this side there will be tensile forces and the compressive stresses will get reinforced because of the bending moment. What about the twisting moment? This is going to create shear stresses in this cross section, and you all know from the design machine element design, all these stresses, the stresses due to the axial load, due to the bending load and due to the torsion which is going to be basically the shear stresses, they all will combine to form the net stresses induced in this particular cross section, and you will have to account for all these different kinds of stresses in the cross section to estimate using an appropriate failure theory, find out what is whether this column is going to survive the stresses induced in the structure. So, this is how migrating from a very basic stress based design, starting from including the static load, the dynamic load will create different kinds of stresses, which is very peculiar to this particular wind turbine nacelle. The design can be made. Now, if you feel that you have taken into account all all the kind of influencing parameters to design this column, we need to be very sure whether we are missing anything on this now. So, what I shall do is, if we really do this design based on only these dynamic forces, we might end up in trouble because we are probably missing an important element here, and that is if this excitation forces which are generated as we discussed in the previous slide, if they get into a situation which generates resonance in this structure, we can have the dynamic response of this column generating deflection several orders, several times the amplitudes which are otherwise expected or planned by the designer. For example, you can see that if the frequency of rotation of this rotor, if I define this as omega as shown here, if it matches with the natural frequency of vibration of this column with all its parameters happens to be equal to the natural frequency, then this ratio of the excitation frequency to natural frequency, if it turns out to be 1, we all know that it is a situation of resonance, and if that happens for a given damping value, we can see that the amplitudes build up to a very large value compared to what amplitudes you would expect if you are operating safely away from this resonance point. So, the point is, if you design this this column based on only the stresses which you anticipate based on certain rotational speed, certain amount of unbalance in the rotor, and think that those are the stresses that will be actually encountered, we need to be little careful in assessing the stress pattern or the stress level in any vibratory system, any dynamic system like this. So, as you can see here, there will be an amplification of the amplitude, and if this column is expected to deflect by a certain deflection, that deflection can get amplified because you would be operating close to a resonance if you do not pay enough attention to the vibration based design, and then in that case the amplitude of vibrations would raise the stress level beyond what you thought it would induce in this particular column. So, that is the reason that closeness of the operating speed to the resonance frequencies can cause unexpected failure, untimely early failures, and that could create problem for us, right. So, in that light, only based on certain forces, based on certain operating conditions are not enough, and you need to pay enough attention to the vibration phenomena if you want to make a solid robust design. Now, one may say that if it deflects maybe 4 times, 2 times, 3 times more than the expected deflection, if you do not bother about the resonance phenomena, so a slight amplitude of vibration should be fine. Why we should be so worried about it? But there is a catch here, and you would all be aware of this graph endurance limit diagram, and in the machine element design you must have learned this, that if we manage to get the stress level induced lower than the endurance limit, you can expect infinite life from the component. Now, you might have designed this column thinking that the amount of amplitude is so much and the corresponding stress is below the endurance limit, and therefore, your life of the component is going to be infinite theoretically, but operating it very close to the resonance or reasonably close to resonance, you are in fact increasing beyond the endurance limit, and that would create finite life of the component. Even if you design this element or any mechanical equipment for certain finite life, calculating that based on your traditional machine element design, the stress level induced is so much, you expect the life to be this much, and that in your application is enough probably. But if you are not aware and your design is not robust enough, then any closeness or proximity to this resonance phenomena will amplify the stress level much higher, and then you will have finite curtailed life. This is the life lost because of improper design, and therefore, we have several situations in the practice in the field that the systems fail much ahead of their design life, and most of the times ignorance of vibration phenomena is the main reason for this. So, this is the reason why we should be mindful of vibration as a phenomena in sound robust design of any mechanical equipment. And as the systems are getting more and more complex, this particular phenomena is going to create more and more trouble in appropriate design of the systems. In fact, there are many case histories where inadequate attention to vibration phenomena has resulted in a longer developmental time, and so those are the examples that are several in the open literature, and therefore, we need to learn this particular phenomena thoroughly and appropriately and include that in our basic design process to get a sound design at the end of the day. Okay, before we take a look at the contents of this course, let me spend a couple of minutes on various applications where vibration has been very challenging aspect of the design process. The aerospace application is one of the most important application where the engines that are there on an aircraft, either it is a civilian or a military aircraft, the engine is the most important element of or a mechanical system in the aerospace structure. And this particular engine what you see here runs at almost like 18,000 rpm, and at such a high speed, vibration of the various elements of this system is a very important and critical part of the design. Apart from, of course, the material challenge because of high pressure and high temperature areas in different parts of this engine, and of course manufacturing problems, the vibration has been one of the bottleneck area, which has many times impeded the design developmental process of this particular mechanical system. And what happens actually, because there are conflicting demands, conflicting demands in the sense that you may notice that this is the rotor of the engine and carries several stages of bladed discs, and these discs are supposed to have very little or very small clearance with the stator, the casing within which this particular rotor spins. For higher efficiency, the gap between the tip of these bladed discs and the stator inner surface is maintained at very small level, and if the vibration of this rotor spinning at such a high speed, the vibration level increases, then the tips of these blades will rub against the stator, and that can create disastrous consequences. If the blades, even if a blade cracks and a part of the blade also flies off at that such a high speed, the kinetic energy associated with the flying blade can be very disastrous in the overall health of the engine. And you can imagine, if an engine fails, what can happen to the aircraft. So, this is one extreme example of where vibrations has been the most challenging part of the design process, apart from other things of course, but the designers really face challenging tasks in ensuring that the vibration levels are within the tolerable limits. The other example here is the space structure. The satellite which takes pictures of the terrain on the earth have cameras which are mounted on the structure, and these camera cannot take high quality pictures if there is even a micro radian vibrations on the structure, because of various components on this satellite structure. There are reaction wheel assemblies and similar other rotating equipment, and if they generate vibrations even with the small amplitude, the vibrating structure can create jitter in the pictures being taken of the terrain. And so that has been a challenging aspect of isolating the camera from such structural vibration. So, even very little small amplitude vibration can be detrimental to the useful operation of the equipment that is in question. For example, this picture of earth taken when there is no blur or no vibration influencing the camera picture taking operation, you can see that the picture is relatively much clearer without any blur, but even small amplitude vibrations can blur the image, and the clarity of the image can get challenged by that vibration influencing the operation of the camera. So, on one extreme you have a very high kinetic energy rotating equipment generating large level of vibrations, and on the other side, even if the vibrations are contained to a smaller value, depending upon the end application, the vibrations can be quite challenging to reduce. On the other side of the spectrum, I am just taking one small example here of a music box. A music box generate melodious sound, but at the base or at the heart of this musical box is vibration at play. The vibration is responsible for generating sound, and you can actually hear beautiful sound, melodious sound Now, how is this sound generated? Let us look at another picture of it. So, if you open the top part of this music box, what you see inside is a vibrating structure at play. Okay. So, what happens is that as you wind the spring which is there, just like our clock, this particular drum rotates at a constant speed, and I will show you how it rotates. It rotates and it excites a set of cantilevers. As you can see, one by one different cantilevers are being pulled up and then they are released. So, the cantilevers vibrate in succession, and those vibrating cantilevers are essentially generating sound. Now, the projections that you notice here on the surface of the drum, they have a job of pulling the cantilever and then suddenly releasing them, so that a particular sound is played, and their position along the circumference and across the width of the drum is properly designed, so that a specific cantilever is excited. And if you notice clearly, these cantilevers have different lengths, and depending upon the length of that cantilever, the frequency is generated. A specific sound of a specific frequency is generated based on which particular cantilever is excited. So, this is how a vibrating cantilever essentially generates sound of the desired quality, and that is how we design this vibratory system to generate specific sound. Okay. So, these are couple of or three different application examples that I highlighted here, which tells you a wide gamut of application of the vibration phenomena. Now, before we start looking at the contents of the course, this is the slide that gives you an idea about the need and importance of studying vibration as a phenomena. I'll just list down few points which will give you an idea about what is it that we need to learn vibration as a separate subject, and how it is important for robust design. The first example is, again I am taking an example of a turbine, now this time a steam turbine. Steam turbine has many stages of bladed discs, just like the gas turbine we saw, and steam at high pressure and high temperature flows across these blades and imparting its energy, the thermal energy gets converted into mechanical energy. And these blades are long, many times freestanding blades, and these blades are a typical vibratory system. Okay. And then if you want this particular turbine to operate for years together, the stresses induced in all of these blades and all of these discs, those need to be within the limit, so as to have an appropriate endurance limit and a good long life. These turbines are expected to run for at least 20 years or more, and usually these turbines are not required to stop for years together, and that is sometimes is the requirement. So for a robust design, you need to design these elements of the mechanical system, ensuring that the vibratory stresses are within limits and they do not cause reduction in the service life or the design life. And therefore, in the design of such turbines, rotors and the blades, vibration plays the most important aspect to be considered apart from the material parameters. For a quieter machine or structure leading to a safety and comfort, so you would all agree that compared to the vehicles or automotive systems of yesteryears, the demand from the customers or users have increased, and the customers are demanding more comfortable rides, quieter cabin conditions, and that requires you to consider the vibration and noise issues in most of our automotive systems. And so, the example that you see here is the most comfortable, quieter kind of a vehicle, and it is the result of concerted efforts to reduce vibrations at the source, that of the engine, and the transmission to the cabin. So, the entire machine structure, the mechanical equipment which drives these automotive systems, their design is done with noise, vibration parameters in mind. So, to give quieter and comfortable equipment and the customer goods. This is just one example. There are many examples such as day to day household items such as washing machines, refrigerators, and so many other equipment which has mechanical devices. A quieter and vibration free equipments are required, and the customers are demanding such systems, which puts a lot of onus on the designers to design them right in the first place, considering vibration as one of the most important parameter. Then many times the machines or equipments are also designed to satisfy standards. For example, a pump that you see here in this picture is not only enough to it is not enough to simply design this for a given flow rate and a given pressure requirements, but they are also designed right at the design stage to satisfy some standards. Like for example, pumps are typically designed to satisfy standards such as American Petroleum Industry Standards, API standards, and then in that sense the designers are not only supposed to understand the basic things, but also vibration based design aspects, and therefore you, if you want to be the designer, have to have an in-depth understanding of vibration as a phenomena. Then for monitoring machinery health or structural health, the bridges and many critical equipments nowadays are continuously monitored for any deviation in their performance or parameters which define the health condition, right. For example, aerospace structures or even flying systems such as a helicopter, and there has been cases of untimely failures, catastrophic failures resulting in loss of lives, by lives in that resulted because of the crash of similar equipment, right, or systems. So, in that case what happens is that if you are monitoring the condition of various mechanical equipment such as gearbox or rotating shafts, and if they indicate deviation from a standard or a limiting or healthy conditions, we can immediately take corrective action and maintenance activities can be properly scheduled. So, there has been instances where early warning symptoms were ignored and resulting into loss of lives. The other aspect of vibration is linked to the product quality, and an example that I am showing here is a typical grinding machine tool, where a grinding wheel here removes material from finishing process on a component, maybe a crankshaft of an IC engine. If it is to be properly finished using grinding operation, you all know that the grinding process removes very little micron level material from the surface of the workpiece, and this grinding wheel is nothing but a rotor with which is carrying a grinding wheel at the end, supported on bearings at certain locations. Now, this is typically a vibratory system, a rotating system which can vibrate under the action of residual unbalance or even cutting forces. Now, if this grinding wheel starts vibrating with micron level vibrations, and if your cutting process is removing micron level material, then the vibration itself may generate additional material removal, and the accuracy of the parts produced can get seriously compromised. So, ensuring product quality will also need a high level of vibration reduction and almost vibration free equipment. So, these are all various examples or points to remember, which points to an importance of vibration as a topic to study and to be seen more carefully, and the design has to be has to account for vibration to develop a robust, comfortable and safe equipment, and that is the reason why we should look at this phenomena closely and understand various aspects of vibration. And now is, I think, the time to start looking at that. Now we have understood that it is indeed very important to understand vibration phenomena. We would like to now take an overview of what steps are typically involved in the overall analysis of any mechanical system. So, this slide is going to put in place an overall general approach to vibration analysis, and with that process we would understand the elements of the vibration theory, which we need to undertake one after the other as we go along in this course. So, an example here I am taking is an automobile, as you see here, with a rider on top. We shall now look at what are the steps in vibration analysis if we are supposed to investigate a vibratory system like this. So, what we have in this picture is a physical dynamic system, and this physical dynamic system, if you want to analyze for its vibration response. So, maybe what I would say is I am interested in knowing what is a vibration in the vertical direction that this chassis can generate for a normal operating condition of this vehicle. Okay. So, if this engine is operating at certain speed, even when the vehicle is not moving, if it is just standing, we all know that even if it is idling, it will generate vibrations in the structure, and that you can definitely feel on the handlebar. So, if my intention is to find out what is the vibration which is generated on the chassis or at the seat position, how much will that be given all the parameters that can be obtained. Okay. So, the first process, if this is the objective, is you can't find that out from an actual physical system like this. So, the first step in this case would be to convert this physical system into a simplified vibratory model of this system. Okay. So, what we would like to now do is represent this physical system as a simple vibratory model. Now, based on my intended objective of this analysis, if I am interested only in finding out what are the vibrations vertically up and down of this particular chassis structure of the automobile, I might, as a first approximation, convert this physical system into a vibratory model as you see here. So, what I have done is I have presumed that this entire chassis, which is an assemblage of several elements here, can be treated like an inertia, and the mass of this chassis is approximated as m e. Whereas, you may notice here that the wheels are isolated from the chassis, or the chassis in fact gets isolated from the ground by the shock absorber or the isolators, and there are two of them, one is on the front side, one is on the rear side. If I quantify the flexibility of this isolator or an absorber. This is the kind of absorber that you have, shocker you call in practical terminology. There is a spring that that gets compressed as the movement from the ground happens through the wheel. So, it is possibly it is possible to model this as a simple spring, as you can see here. So, I am just representing this physical objects in the form of some elements of a vibratory system. In this case, the spring in the shock absorber is modeled like a coil spring here with a stiffness K equivalent, and there is also a damper or a dashpot in parallel in this system, which I am representing as a dashpot whose parameter is C equivalent. So, that is the dashpot constant or a damping coefficient which represents the property of this dashpot. We know that the spring is quantified or characterized by its stiffness or spring rate. So, in this case K equivalent happens to be that spring rate, and on top of this is sitting a mass which is representing the chassis of this automobile. So, what I have done here as a first approximation, I have clubbed the characteristic of these two suspensions or shock absorbers into a one single stiffness element and a damping element, and the chassis is modeled like a simple point mass which is sitting on top of it. Now, how do we get these parameters is a different thing, we will discuss and figure it out later, but because the objective here is to highlight and have a overall view as to what are the process or steps involved in the process of vibration analysis. This is obviously the first step in the process to get a simplified vibratory model. How simple depends on what is your objective here, what exactly you want this model to give you, and if it is only a vertical motion, then obviously along with these elements I would specify what is the degree of freedom or in which way this mass or an inertia element is going to move. Now, of course, this mass can translate in this direction, it can oscillate and all of that, but as a first approximation, if I am interested only in the vertical vibratory motion, which could be an important consideration for the driving fatigue of the passenger or a rider sitting, then I may consider as a simplified case or a simple case x as its degree of freedom or a vertical motion as its degree of freedom, and then this model as an approximation of the physical dynamic system is complete. So, this vibratory model, once it is done, that is the end of the first step, but what do we do with this model? Because if you want to find out what is x of t, we need to go beyond just the model which we have realized. So, obviously, as you would agree that you will have to have apart from all of these all the possible forcing functions or the excitation mechanisms on the structure. So, maybe I will specify that forcing function as the force. Where would it come from? This system, even if it is stationary and standing idle, but the engine running, we know that it vibrates. The vibration essentially comes from the engine. So, from the engine source, if I somehow characterize what forces are generated in the engine, then I have a forcing function that is going to act on this chassis and therefore, on the mass m equivalent. Once this is done, to get x of t, I need to somehow go one step beyond. The second step involves generating governing equations of motion. So, equations of motion that will give me x as a function of time, and that if I get, I can plot this response which is x as a function of time. As time evolves, how much is the amplitude x as a function of time, that will give me the basic vibration output from which I can draw inferences or conclusions. So, the idea here is now from this simplified vibratory model, I need to get the governing equations of motion, so that I can then solve these governing equations to get the response of the chassis. Okay. So, how do I get the governing equations of motion from a vibratory system which whose model is given here? So, obviously, there are many ways through which you can do it, but the simplest and particularly convenient for simpler systems is simply to apply Newtonian approach, where you get a free body diagram of this mass and look at what forces which are going to act on this free body as it undergoes dynamic motion. So, if I assume that this mass moves with a displacement, velocity and acceleration whose positive direction I have presumed in the vertical direction, then with that what are the forces? So, if I strip this body from its surrounding, what are the surrounding what forces do the surrounding act on this isolated body? So, we call this as a free body diagram, and all of you have learned this process of getting a free body diagram and identifying all the forces which apply on this free body. Once you identify that, you can apply Newton's second law to find what are how you apply that is by writing an equation like this. Typically, all the forces in the direction of acceleration are equated to mass times acceleration, and the forces which act on this free body are sum total of all the forces that I have identified here. So, if you strip the body from the surrounding, the damper is going to act its force on the body, and that obviously if the velocity is positive upwards, the dissipating force, the dash pot force is going to act in the opposite direction, and we will discuss these forces how they apply later, but this is how all of these forces are shown on the free body. And so, you find out what is the net force which is acting on this free body. So, it is going to be f of t minus c equivalent x dot minus k equivalent into x, that is the net force in the direction of acceleration. By equating this, you will get the governing equation of motion. Of course, there are a couple of other alternate ways of getting this. Energy methods is one of them, which of course we will deal with later, but as a process, step 2 is getting the governing equations of motion, and one of the common way of doing that is apply the Newtonian approach, and with that you can easily get a differential equation like this. X dot, by the way, and x double dot are the time derivatives of the vibratory displacement x of t. So, with this governing equation obtained by applying Newton's law, it is quite straightforward now. For the next step here, just getting the governing equations is not enough, you have to solve these governing equations, and once you solve this, basically you will solve to get dependent variable x obtained in the as a function of the independent variable time. So, of course, the displacement x as the degree of freedom of this mass is going to be dependent only on time, and we would then obtain the response x of t, and that basically is shown here. So, if you solve it, how we will solve this and how that process is, all of that is going to be the subject matter of discussion as we find this out in the discussion on single degree of freedom system. But trust me, this is how the equation will the governing equation will get solved, and finally you will get the solution to be x of t given by this this expression. This of course with the assumption that the forcing function here f is given by some f cap cos omega t or sin omega t and so on. So, with that this is how the solution will be obtained. So, once you solve this, you can get all the I mean the displacement of this chassis at all the time instances, and once the solution is obtained, the final step in this whole process is going to be of interpreting the results, right. So, for example, if I plot this x of t for certain parameters, I might get a response for a given excitation frequency or omega given by this response. So, this response tells me that the amplitude of vibration as this mass vibrates is given by this response curve as a function of time, and then I would then based on this response obtained interpret why we are doing this vibration analysis process is to have a robust design and to cross check the design and so on. So, how would this response assuming that you will get this expression solved for all the parameters that you have extracted from this physical system, and finally the response turns out to be this. How do you make out of make any sense out of this particular response history? What it tells you, just to take it I mean to emphasize what interpretation mean or how to use this response output for the design process. One of the simpler thing is I get the value of the amplitude with which this chassis is going to vibrate. Now, we know from this analysis by putting appropriate values is, let us suppose that this amplitude peak value is turning out to be maybe 21 millimeter amplitude. Now, one of the very simple and straightforward way to make use of this response obtained response from the analysis is to look at this spring. If this spring is in the form of a coil spring, which is mostly the case, most of these two wheelers you will find that the isolator or a suspension is in the form of a spring. Now, if the you all have done the design of spring, or in your theory of machines you might have seen what is the pitch of the spring. Now, if the clearance in the two adjacent coils is let us say 15 millimeters, then such a large amplitude is going to cause closure of the spring, and then it becomes solid and it is no more acting like a spring actually. And so, it would be important for you to interpret this result from the context of your element design and use that input for redesigning all your systems. So, if the stroke length of this dashpot, the piston is limited to 15 millimeter or 10 millimeter, and if your vibration amplitude from your theoretical study turns out to be way beyond that value, then you have to go back to the drawing board and redesign them so that the vibration amplitude is reduced to a significantly low level, so that this works as you have designed it for. Okay. So, in addition to that, this amplitude of course is obtained for a given operating speed of the engine, let us say omega, and suppose this automobile is going to operate at different speeds of rotation, then it would be also interesting and important to assess this vibration amplitudes at different operating speeds. So, you might end up in generating this response as a function of the frequency. So, so at different operating speed given the same system with the natural frequency omega n, you might like to figure out what if this operating speed spans from this value to this value, what are the maximum level of vibration amplitude that it is going to generate. So, this graph, which is basically giving the response at different frequencies, would be an important output that you would like to generate, and based on that response curve you would like to interpret that data from the context of the design that you are doing for the automobile. So, this is all what I wanted to highlight regarding interpreting the results. Of course, there are many things that are to be interpreted, and as we go along in the course, I would make it a point to discuss the results that we are getting from the context of the mechanical system design. So, for example, this entire vibration analysis process, as it starts from the step 1 of getting the vibratory model, step 2 getting the governing equations, which we finally solve to get the response, vibration response, and finally once the vibration response in different type or different representation format that we get, how do we interpret the results obtained from this analysis. All of these steps are very important and essentially gives you a glimpse of what is in store for when you do the vibration analysis of any mechanical equipment. Now, if I ask what would be the most challenging out of all the 4 steps here, it definitely is the first step, which is going to be the most challenging one. Why? Because it's not that straightforward to get a physical system converted into an appropriate vibratory model. In fact, there is no unique way or a unique process or a unique model in fact for a given physical system, because somebody can model it differently, and in fact the final objective of this vibration analysis process actually dictate what kind of a model that is required to be built, and it takes some experience and expertise to figure out how this physical model is to be captured as a simpler vibratory model. That process definitely, as I said, is not so simple for a beginner, right. Similarly, unless you understand the entire vibration analysis, interpreting the results can also be tricky. We have seen the simplest of it in the context of the spring design, but there are many complex systems for which this output would have to make sense, and for that experience again plays a role, and more important than that is a very correct fundamental understanding of the vibration phenomena is equally important. But if you look at the other 2 steps, like once you formulate this model, getting the governing equation from this model is reasonably straightforward exercise, because you have been learning about free body diagrams and the Newton's laws and approaches to get the governing equations. Even solving the governing equations, once you get it like in the form of an ordinary differential equation, is a mathematical process which you have learned so many times. So, the steps 2 and 3 are comparatively straightforward ones as compared to the initial step of modeling and the final step of interpreting the results, right. So, what I meant actually is the challenges in the realization of the mathematical model through the vibratory model is the fact that somebody can model this same automobile in the form of a little more involved number of mass elements. As you can see here, I can instead of a single mass, I can get a mass of the chassis as a separate one, but if this wheel is is going to have a significant mass, and if I want to really investigate this vibration a little more in a more accurate way, I would for high speed high speed traveling automobiles, I would definitely would like to model the wheel itself like a mass. So, this isolator or an suspension element would be separating the wheel and the chassis as also the dashboard, and I can then model the flexibility or compliance of the tire as another spring, and I can model the tire itself as a spring element, which will capture the flexibility or the compliance that any tire that has been designed in the form of a spring here. So, a tire gets modeled like a spring, the wheel model like another independent mass, because the wheel can vibrate irrespective of the way the chassis is vibrating. Okay. And then of course, I need to also understand and ensure that the suspension which is in the front wheel is of a different nature or a character as compared to one at the rear wheel. So, obviously, the properties of these springs and dashboards would be different at the front and the back side or the rear side, and therefore, it makes sense to model them individually through the individual wheels here. That will give me much better and accurate picture, or I will be able to capture the dynamics more appropriately than what I possibly could in the previous case. Not only modeling these as different elements, but also finding out the appropriate degrees of freedom for each is also very important. For example, if you might have seen that if I suddenly brake this automobile when it is moving forward, it is not that the chassis just dips down and vibrate vertically, but you all have experienced this, that it will pitch, it will oscillate about an axis here. So, the whole chassis will swing in the vertical plane, which means that it is not only going to have a vertical motion, but it will also have a swinging motion or a pitch motion, and therefore, apart from x as the degree of freedom, I might introduce another degree of freedom, the angular deflection of the chassis suspended, and therefore, apart from the vertical vibratory motion x, I would be introducing a pitch motion, a theta degree of freedom to this chassis. Of course, the wheels are very less likely to have those kind of motions. So, the wheel is expected to be only moving vertically up and down. The reason why based on the reason that it is connected to the suspension the way it is, only 1 degree of freedom suffices for the wheel, and then you have 2 degrees for the chassis and 1 each for the 2 wheels. That makes it 4 degrees of freedom for the same automobile. So, what you can see here, that the first step that we thought of as the first step for getting a vibratory model, the first step itself can be quite tricky, and many multiple models can get derived out of the same physical system. It all depends upon finally, if you are interested, also getting to know how much is the pitch that the vehicle is going to get subjected to from the ride viewpoint or ride comfort viewpoint, and if the tires do have significant influence on the dynamics, you can include the tire stiffness here and so on. So, the first step here is obviously the most challenging and quite involved one, but once you get this model made, rest of the process is quite straightforward. And in this particular course, what we are going to look at is how each of these steps are actually realized, how a model is made, once a model is made, how the governing equations are obtained, how do you solve it, and what response features that you get out of solving these governing equation, and how to make sense out of these response values that you have got, and looking it in the context of the overall system design. That is the entire vibration analysis process that we have for you. And in the next session we would then look at the overall course content that I have divided this into, and then we will get started with a single degree of freedom system, the very basic fundamental theory of vibration. Okay, the summary of this first lecture is that what we learnt in this lecture is the need and significance of vibration based design, and also how a typical vibration analysis process is carried out.